Human-robot collaboration. The augmented age is characterized by the current transition from pure logic technologies to intuitive, neuromorphic artificial intelligence. Augmented cognitively, physically, and perceptually, as the world is significantly more connected, with greater complexity and more adaptability. Intuitive thinking machines, the next stage of Industrial Revolution 4.0, is characterized by exploring and applying artificial intelligence through neuromorphic architectures in order to emulate the biological neurons and synapses of the cortex human brain. The brain has millions of neurons. Each forms synapses or connections with each neuron. Synaptic activity relies on ion channels which control flow of charged atoms. The neuromorphic architecture copies this model by connecting a web of artificial intelligence neural network transistors that mimic activity of the ion channels. The 21st century is an exciting time for engineering innovations as it relates to artificial intelligence in the universe of robotics, research, and development. My goal is to present an engineering turnkey solution regarding the metaphysics of artificial intelligence, machine learning, cognitive, neuromorphic intelligent robotics, as illustrated in this video. These orthogonal digital AI applications are manipulated by a central silicon neuromorphic brain. The central neuromorphic brain, CNB, is integrated by an AI cloud computer system architecture. Human-robotic collaboration is common practice by intuitive of deep learning machines transitioning to cognitive and convolutional neuromorphic artificial intelligence. My objective is to illustrate and to show several engineering prototypes. These engineering models form part of the augmented age of machine learning artificial intelligence and the Industrial Revolution 4.0 paradigm. The prototypes included are three-dimensional printers and an industrial lathe and milling machine systems. These orthogonal digital AI applications are manipulated by a central silicon neuromorphic brain. The new evolution of quantum technology enables humans to take a giant leap in the development of modern three-dimensional printing digital platforms. Essentially, these new robotic digital platforms will enable engineers to create and to manufacture mechanical parts and components and to develop biological human organs in the area of microorganisms to improve the human condition. The new paradigm encapsulates physical, biological, and digital systems. The objective is to design a cost-effective 3D printer. Here I illustrate the assembly and manufacturing process of the proposed 3D printer prototype. The 3D digital platform is integrated by orthogonal architectures consisting of a RISC processor board and an analog motor controller or servo controller circuit board. A power supply is used to supply power to the motor controller circuit board. Python software consisting of G-code and several mathematical algorithms in order to control the servo motors. The code controls movement and calculates vertex positions of the motors in the X, Y, and Z direction. CNC, which is the industrial control application. These are the patterns generated in software so as to provide a specific solution to your final tasks. C++ 3D software modules are used so as to develop the desired 3D models. Additional algorithms are used to provide solutions for your tasks and objectives. The 3D digital platform includes the firmware to provide a full turnkey custom-fit solution. It consists of a RISC processor board and an analog motor controller or servo controller circuit board. The code controls movement and calculates vertex positions of the motors in the X, Y, and Z direction. The Python software modules provide the control environment in this industrial application as it relates to the lathe and milling systems applications as viewed in this prototype. You can call the G-code within the CAD/CAM industrial simulator. The CNC simulator shows movement of 3 motors running in X, Y, and Z direction. The system displays the pattern generated by the G-code, and the CNC simulator performs the milling system cutting tasks. The Python software modules provide the control environment in this industrial application as it relates to the lathe and milling systems applications as viewed in this prototype. I have presented an artificial intelligence digital platform. The platform is integrated on an industrial lathe and milling machine. The lathe and milling smart system was used to create and to develop the artificial intelligent cognitive industrial robotic arm, as it is shown in the following video segment. My goal is to present an engineering turnkey solution regarding the metaphysics of artificial intelligence, machine learning, cognitive neuromorphic intelligent robotics, as illustrated in this video. The robotic arm presented in this video is an artificial intelligence system with generalized human cognitive abilities so that when presented with an unfamiliar task, it has enough intelligence to find a specific solution. Artificial intelligence is the simulation of human intelligence processes by machines, especially computer systems. These processes include learning, that is the acquisition of information and rules for using information, such as reasoning, using rules to reach approximate or definite conclusions, and self-correction. Specifically, AI includes expert system speech recognition and machine vision. 7 servos provide 6 degrees of freedom, allowing countless robotic arm movements. The arm has a swiveling base, shoulder with lifting servos, elbow, wrist, and rotating gripper. The artificial intelligence digital controller has a 16 servo controlling mechanism with its own internal firmware and software mathematical algorithm. The AI smart robotic arm includes software that manipulates the servos and store sequences of all positions. A sequence of up to 60 positions can be downloaded and stored in the servo controllers so that the robot arm can move without being tethered to a computer. The artificial intelligence servo motors are controlled by sending a series of pulses through the signal line. The frequency of the control signal should be approximately 50 megahertz, or a pulse should accurately occur every 20 milliseconds. The width of pulse determines angular position of the servo, and this type of servos usually rotate 180 degrees. They have a physical limit of travel. The firmware resides on the main digital platform. Machine learning integrated. Motor software. Here is an illustration of the software models which activate the motor movement. The software is created with C++ and Python, integrating solutions for pulse width modulations by controlling several analog ports located on the main computer digital platform. You have viewed several industrial robotic engineering prototypes in this video. These engineering prototypes are based on artificial intelligence, narrow AI, and artificial general intelligence. That is smart robotic systems with cognizant ability, capable of performing manufacturing repetitive tasks. Within the next 100 years, there will be a super cloud computer system capable of controlling billions of robotic systems, providing solutions and accomplishing every task on planet Earth. Artificial intelligence is getting smarter by leaps and bounds. It is projected by end of this century that an artificial intelligent computer will be as smart as a human being.